All right, welcome back everybody. We're going to start with this example because it's a little bit non-trivial and I don't exactly like the way that the book introduces it. And basically the idea is that we want to convert this vector field, which is in Cartesian coordinates, into a cylindrical vector field. And the way we're going to do this is jumping back to linear algebra. So we're going to reinterpret this vector against the basis rho, which is x over root x squared plus y squared, y over root x squared plus y squared, 0, and theta. I'm not going to write out the z basis because of course that's trivial, but the theta basis is this one, y over root x squared plus y squared, and x over root x squared plus y squared, and 0. And the z basis is, I guess I'll write it out just for you all, 0, 0, 1, right? So we're going to reinterpret that way, and if we remember from linear algebra, the way that we do that is we take the dot product. So we're taking, we say that V cylindrical equals the dot product of V with rho dot, or rho vector, times the rho vector plus the dot product of V with the theta vector on the theta vector plus the dot product of V with the z vector on the z vector. That's the traditional way we would actually convert from one to the other. So let's go through that. And to do that, I'm just going to jump to the whiteboard. So V Cartesian was, let's see, minus y over root x squared plus y squared. It was x, it was not a root on the bottom there. Minus y over x squared plus y squared. It was x over x squared plus y squared, and then 0. If I compute V Cartesian dot rho, I end up with minus xy over x squared plus y squared to the 3 halves plus xy over x squared plus y squared 3 halves, and the xy's cancel and give me 0. If I compute V Cartesian against theta, I gain, I suppose that's y squared over x squared plus y squared 3 halves plus x squared over x squared plus y squared 3 halves. And now my numerators add together and I gain x squared plus y squared, and they're going to cancel with exactly 2 of the 3 halves in the denominator, so I end up with 1 over root x squared plus y squared. And finally, it's not that hard to see that V Cartesian against the z is exactly just the z element, 0. Okay, so now these are my 3 coefficients. If I wanted to write V cylindrically, I would take 0 and then 1 over root x squared plus y squared and then 0, and those are my coefficients against each of the vectors. But if I want to reinterpret, maybe I want to write everything in terms of cylindrical coordinates in this setting as well, and I can do that with 1 over root x squared plus y squared and just rewrite that as 1 over rho on theta hat, or interpret it as a vector that's 0, 1 over rho, 0. But this is a cylindrical coordinate vector. So that's the way I like thinking about this a lot better than what the book has. You can definitely interpret the way the book has it just as well if you want to. But that's why you see the answer that the book got to 1 over rho is just like the one I just got. Okay, now we'll move on to integration in cylindrical coordinates. We're going to move truly to calculus now. And it's important that we talk about integration in higher dimensions under a change of variables. So traditionally, we would just write our region omega in a higher dimensional setting, and then we have dx, dy, dz. But unfortunately, if we change our variables, suppose d omega, it can be written as d of some region in x, y, z. That's the traditional way, but we can change the variables of the region x, y, z now to cylindrical. We have a region in rho, theta, and z, and all of a sudden the coordinates there, dx, dy, dz, are going to have to change in our new region, and that's because when we calculate volumes, we naturally, I should say this is the natural volume calculation, right? We naturally say everything with a volume has a length, a width, and a height, which is exactly what dx, dy, dz means. We don't say things with a volume have a radius, an arc, and a height, which I guess is what rho, theta, and z are, right? So we have to account for the radius, the arc, and the height transition that we would make if we are going to be in cylindrical coordinates. So let's move on to see how we actually take control of that. And if we were to take calculus 3, we could actually derive this ourselves if we want to, but the way it gets derived is that our transition operation, that's what we're calling t, from an xyz coordinates looks like rho cos theta, rho sine theta, and of course z remains as z. Those are the transitions. And so if we're coming through here with a d, right, and we're coming through, there's dx, there's dy, and there's dz, then really I'm calculating d rho cos theta, d rho sine theta, and dz, so that this actually looks like now under the product rule, cos theta d rho plus, I guess that's sine theta, so rho sine theta d theta, and then I recover sine theta d rho plus rho cos theta. I guess I'm missing a negative in the above. This is negative rho, if I calculate things correctly. Rho cos theta d theta, and then I gain dz out of this. And so this is now what our three differentials of width, length, and height look like in cylindrical coordinates. And thankfully, what we end up doing when we calculate volumes is we multiply each of these coordinates together, right? And so in fact, we're going to multiply each of these together and multiply each of these together. And under some simplifications, we recover something that's a little bit easier. We can represent the transition by this Jacobian, by the way. But once we multiply them together, it turns out it all simplifies to rho. And then I should say our dx, dy, dz, the rho here comes through as basically what is the extra term we need to account for, d rho, d theta, dz. So there's an extra term we need to account for of exactly rho when we multiply them all together. And this determinant, by the way, is just playing the same role of multiplying all of them together. You can see if I took the determinant of this 3x3 matrix, that would basically be the same as me doing that multiplication from earlier. So you'll notice I get rho cosine squared plus rho sine squared, and that gives me exactly what I want. Okay, so this is really what we want to memorize today, right here. So transition from Cartesian to cylindrical in integrals is we're going to take dx, dy, dz, but we're actually going to write that as rho, d theta, dz. All right, so let's actually compute one of these. It's the next example. So this integral, we already talked about how in the last lecture, this f, if we wrote it in cylindrical coordinates as rho theta z, can be rewritten as z over rho, and that's very useful. And then if we think about this region that it's describing, the solid cylinder of radius 1, z-axis, and 0 to 5, let's just draw that out so we have a good idea of what we're actually calculating here. So z starts at 0, z ends at 5, radius is 0 to 1, because rho equals 1, z equals 5. And it's very clear from that theta should go the full circle, which is 0 to 2 pi. Then we can set up our integral here in terms of rho theta, so f of rho, theta, and z. Don't forget we're adding a rho in, rho d theta dz. And we just ask ourselves, what are the bounds that rho, theta, and z need to take? Well, rho goes from 0 on the z-axis to 1 at its peak, at the edge of the cylinder. Theta goes from 0 to 2 pi, and finally z goes from 0 to 5. So that's how we're going to set up our integral, and if we simplify this a little bit, that's really the integral, 0 to 1, f of rho theta z, well, that's z over rho multiplied by rho because we have that rho there, and we just get z d rho d theta dz, and of course the two terms in rho and theta are not going to care about anything. Rho and theta. So rho is just going to give us a 1, theta is going to give us a 2 pi, z is going to give us z squared over 2 from 0 to 5. So we end up with something like 25 pi. 25 pi here. Now I'm going to scroll down and we're going to see that hopefully the example agrees with me. So here we go, scrolling down, we see it set up and we get to 25 pi. So there you go. So basically this integral, we wouldn't have wanted to calculate this in Cartesian coordinates. Once again, it comes down to like a trig substitution if you were actually going to calculate the x's and y's integrals here. And you notice by switching to cylindrical coordinates, our integral was very easy. So that's kind of the beauty of integrals in cylindrical coordinates. If we move on to derivatives in cylindrical coordinates, these actually get a little bit easier than the integrals, I think, anyway. We can look at maybe the gradient of a function. And the gradient of a function in Cartesian coordinates, we have three directions we can take derivatives in, and we exactly extract those derivatives, but we have to modify in cylindrical coordinates because I think you can probably remember this when we were considering curves in cylindrical and we took their gradient, or we took their time derivative, we recovered rho dot, but then we recovered rho theta dot and then z dot. And so this middle term, rho theta dot, says that as I move in the theta direction, which is that, as I move in the theta direction, I actually have to recover multiplication by rho on specifically the theta term, right? So the d theta, the rho d theta there is just like rho theta dot. And this is, once again, if you missed it on the last video, because of angular velocity. Because angular velocity depends on the radius which one is sitting at. So you can imagine if I've pushed my radius really far away from the origin, then the total angular velocity of some scalar field is probably reduced really far because the scalar field is not changing much in a rotational aspect if I'm really far away from the origin. Right, my rotation has been damped down. And so that's really why we're dividing by rho right there. So that's the special thing to keep in mind with gradients in cylindrical coordinates, CYL. We have to divide by rho, specifically on the angular term. Let's jump to the whiteboard and just do a quick example. So f, let's say of rho theta and z, let's call it rho cos theta plus rho. Okay, and then I can calculate the gradient of f in cylindrical coordinates as it's the derivative in rho, which gives me cos theta plus 1. Then I have the derivative in theta, which gives me rho, negative rho sine theta plus 0, but I have to multiply by 1 over rho. So once I multiply this by 1 over rho, things change a little bit. And finally, the derivative in z is 0. So if I simplify, then it turns out the gradient of f in cylindrical coordinates still is cos theta plus 1, negative sine theta, and 0. There's a nice example of gradient in cylindrical coordinates. Let's jump back to the book. The last step I want to talk about is the Laplacian in cylindrical coordinates, because if the Laplacian is the gradient dot the gradient, and the gradient in cylindrical coordinates is modified, then the Laplacian in cylindrical coordinates is the gradient in cylindrical dot the gradient in cylindrical. If we actually go through that dot product, we recover the following. So unfortunately, there's a little bit of an ugly term here where we actually have rho multiplying partial f partial rho, and then we take partial rho of that term and divide by rho. And then on the angular term now, since we've gotten angular squared, we're dividing by 1 over rho squared. I'm going to expand this right now to make everybody's life a little bit easier. Let's expand the product rule here, because this actually makes our life a little bit easier if I expand the product rule. So derivative of the first part, so derivative on rho is just going to give me 1 over rho partial f partial rho, and then derivative on the second part gives me partial squared, and then these cancel, so I get partial squared partial rho squared f plus 1 over rho squared partial theta squared f plus partial squared partial z squared f. And so this is maybe the way I like thinking about it a little bit better, is we account for 1 divided by rho squared on the angular term, and then we pick up this interesting cross term, which is 1 divided by rho partial f partial rho. So let's just go through that really quick, a nice example on the whiteboard. Let's go with the same scalar function, f of rho theta z. Scalar function was rho of cos theta plus rho, and if I'm calculating the Laplacian in cylindrical, recall that is 1 over rho partial rho plus partial squared partial rho squared plus 1 over rho squared over partial theta squared plus partial squared over partial z squared. So if I'm calculating now the Laplacian and cylindrical coordinates of f, I'm going to take 1 over rho partial rho, and that gives me 1 over rho cosine theta plus 1. I have partial rho squared. Notably, everything is going to go to 0 then. I have 1 over rho squared partial theta squared. That's going to give me 1 over rho squared. And then if I take one partial theta, that goes to minus sine. If I take another partial theta, that goes to minus cosine. So I have rho minus cosine theta. And finally, partial z squared is 0. And so if I simplify this out a little bit, I end up with here, that's negative cosine theta over rho. Here I have a positive cosine theta over rho, and all I'm left with, because that and that cancel, all I'm left with is 1 over rho. And so you can see that the Laplacian behaves a little bit differently in cylindrical coordinates. I want to check. We'll check really quick, right? Because 1 over rho is 1 over root x squared plus y squared. Let's just check really quick on Wolfram whether or not the Laplacian of f, now in Cartesian coordinates, where f is represented as x plus root x squared plus y squared, agrees. So we're going to head over to Wolfram really quick. Okay, welcome to Wolfram. I'm just going to define f of x, y, and z as what we saw earlier, which was x plus square root x squared plus y squared. And now I'm going to calculate the Laplacian, which is, I'm going to simplify it just to make sure everything looks right, d of f. I'm going to take two derivatives in x, d of f. I'm going to take two derivatives in y, d and f. I'm going to take two derivatives in z. And you'll notice this is exactly what we had found when we did the Laplacian in cylindrical coordinates. So everything does work out, even though it looks a little funky. Anyway, that's all I have. I'll see you in class. Bye.